Hello, this presentation is about a common drug compound that is used as an anticoagulant or blood thinner in the body. It is used to treat or prevent the formation of blood clots in both veins and arteries, which can ultimately reduce the risk for having a heart attack or stroke. The name of this compound is warfarin.
The structure of warfarin can be seen here. This molecule has a molecular formula of C19H18O4 and a molecular weight of approximately 308.333 grams per mole. Looking at the structure directly, we can see that there are three six-membered rings, two of which are benzyl rings, and one of which contains an oxygen atom within the six-membered ring. There is also the presence of an ester functional group, a ketone, as well as an alcohol group.
The active form of the drug, or the form that is given to patients, is in its sodium salt form. As we can see, the alcohol group has been deprotonated and the counter ion associated with it is a sodium ion to stabilize the negative charge on the oxygen. The sodium salt is sold to consumers and patients in a racemic mixture. The structure of the molecules only has one stereocenter, and so by flipping the stereocenter at the one carbon, a racemic mixture of enantiomers is formed.
The S enantiomer of the warfarin salt has been found to be 3 to 5 times more effective in its anticoagulation effect than its R enantiomer counterpart. This is because its S structure allows for a particular enzyme, CYP2C9, to metabolize it faster, causing its clearance from the body to be much faster and its anticoagulant effect to be much more efficient than the enzymes which react with the R enantiomer.
Another physical property derived from its structure is its high solubility in water, 17 milligrams per liter. Due to the negative charge on the oxygen, the negative charge interacts with the strong polar water molecules, allowing hydrogen bonds to form and thereby quickly dissolving in water. Analogous to this, warfarin salt is also highly soluble in blood due to the fact that blood is polar and is also made highly of water. This means distribution throughout the body once it reaches the bloodstream is fairly fast.
In solution, warfarin has been seen to tautomerize to form a cyclic hemiketal through a reaction between the ketone and the 4-hydroxy group. However, further studies with similar anticoagulants have shown that the active structure of warfarin is the original tautomer.
Lastly, warfarin's other physical features include that it is as colorless a crystalline powder, and it has a melting point of 322 degrees Fahrenheit or 161 degrees Celsius. It is not flammable and not corrosive.
As stated before, warfarin is used to treat or prevent the formation of blood clots in both veins and arteries, which can ultimately reduce the risk for having a heart attack or stroke. In order for blood clots to form, molecules called clotting factors are needed. Clotting factors signal each other to cause a chain reaction in which they come out of dissolution and form strands called fibrin that trap platelets in cells, causing a clot to form.
Vitamin K is an essential component of these clotting factors, and so warfarin inhibits the enzyme vitamin K epoxide reductase, thereby preventing the production of vitamin K-dependent clotting factors.
Vitamin K is considered fat-soluble due to its nonpolarity, which allows it to be dissolved by other nonpolar compounds such as lipids. Fat-soluble vitamins are stored in the body longer than water-soluble vitamins, which means that the risk of depleting the vitamin K supply of the body is lower compared to that of other vitamins.
In the body, vitamin K is naturally oxidized into phyloquinone oxide through the carboxylation of glutamic acid. The enzyme vitamin K epoxide reductase functions to reduce the oxide back into vitamin K. This means that vitamin K is constantly changing forms. When warfarin is introduced to the system, it interferes with the vitamin K epoxide reductase, increasing the ratio of oxide to vitamin K. The oxide competes with the action of vitamin K, blocking active sites in the synthesis of prothrombin, an essential blood clotting factor.
Essentially, warfarin changes the intracellular redox state of human vitamin K epoxide reductase, which is how it works to inhibit the enzyme. In one journal, the mechanism of this inhibition was discovered when it was found out that the mutation of two cysteines, an amino acid with a thiol, or SH group, stopped the inhibition of the molecule. This allowed them to conclude that a disulfide, or SS bond, was formed between the two cysteines that was necessary for warfarin to bind to vitamin K epoxide reductase. Therefore, warfarin binds to vitamin K epoxide reductase in a way that is stabilized by the SS bond, as is shown in the image.
When the enzyme reduces vitamin K, each catalytic cycle involves the conversion of two sulfohydryl groups to a disulfide bond. The presence of warfarin does not allow this conversion to occur, inhibiting the enzyme.
In the 1920s, American and Canadian farmers on the Great Plains were plagued by the sudden deaths of healthy cattle due to internal bleeding. The culprit was found to be moldy sweet clover hay that was causing the illness. However, it wasn't until a decade later that research began to find the biological agent after a Wisconsin farmer brought a milk can full of blood from a poisoned cow to the University of Wisconsin. After several years of research, the substance was isolated and patented by the researchers as dicumarol. Later research into natural coumarin derivatives yielded an especially potent form which the group later patented as warfarin in honor of WARF, the Wisconsin Alumni Research Foundation, which sponsored the group.
Warfarin was first marketed as a rodenticide upon its release in 1948 and was met with great financial success. Research resumed into medicinal use of warfarin after the attempted suicide of a U.S. Army inductee using half a gram of warfarin as rat poison. Warfarin then found great success as an anticoagulant and achieved relatively immediate use, with a warfarin derivative being prescribed to President Eisenhower in 1955.
Traditionally, one of the steps in the synthesis of warfarin has been a Michael condensation between 4-hydroxycoumarin and benzyl acetone to form racemic warfarin. 4-hydroxycoumarin can keto-enol tautomerize at the hydroxyl group, meaning an enolate intermediate is also formed. Benzyl acetone is a 1,4 substituted ketone and can perform 1,4 addition with nucleophiles. This reaction thus proceeds according to the image.
When blood vessels are broken in the body, a chain of events known as coagulation cascade occurs. The purpose of the coagulation cascade is to produce thrombin as quickly as possible. Thrombin is an enzyme that breaks down another protein called fibrinogen to form fibrin, the protein that makes up the majority of blood clots.
In order for the coagulation cascade to function properly, a number of enzymes must be in place. Many of these enzymes are formed in part from vitamin K, which is oxidized in a reaction with an enzyme precursor. An enzyme, VKORC, vitamin K epoxide reductase, then reduces vitamin K, allowing it to react again. Warfarin works by blocking the function of VKORC, preventing the reduction of vitamin K. Without a sufficient amount of vitamin K, improper enzymes will be used in the coagulation cascade, resulting in improper thrombin formation and improper clot formation, leading to an overall reduction of clotting in the body.
Thanks.